In this week, we will discuss about micro actuation and micro manipulation, second series, under the course on micro robotics. So, ideally, in this module, we will be discussing about shape memory alloys, conducting polymers, based actuations, slip mechanisms, and the comb drive actuators. Now, let us discuss about this shape memory alloys. As far as shape memory alloys are concerned, it falls under the category of smart materials. Like as you all know, compared to the other materials, these smart materials has certain amount of specific advantages compared to other materials. In fact, it has a specialized functionality in such a way that we can use it for specific applications. In fact, these smart materials has a potential applications in the case of this biomimicking robots, because in the case of biomimicking robots, like it doesn't follow the conventional degrees of freedom. So, in case if it follows the conventional degrees of freedom, of course, motors are used as an actuator for this conventional degrees of freedom. However, in this particular case, when we go for a kind of smart material based structures, like you can program the materials for a biomimicking related application. This is one of the advantage of going for these smart material based structures. Now, if I try to look into the overall requirement of these smart materials, so these smart materials, when we try to integrate these smart materials, this smart materials should have a capability to get interfaced with the sensor, and it should have a capability to interface with the controller. So, what happens is this smart material should have a good hand holding with the sensors and the control system to form a smart system. So, these smart systems are quite efficiently utilized in such a way that, so this can be used for different specialized functional applications. Like for example, if you take a small shape memory alloy based micro robots, these shape memory alloy based micro robots can walk or it can generate a micron steps, which is possibly using this particular systems or particular arrangement. So, like in that aspect, if you take, so whenever we are trying to develop such kind of smart material based structures, so we may need to integrate it with sensors. So it should have a capability to well integrate with sensors and well integrate with controllers. However, there are certain cases where the smart material itself can act as a sensor, as well as it itself can act as a actuator. Now, let me just give you a brief overview about the family of smart materials. So, as far as smart materials are concerned, there are list of smart materials are available, which includes SMA, piezo, hydrogels, ferrofluid structures, then we have the conducting polymers, and then there are also some responsive polymers, pneumatic blaze flexible materials. So, like this, many such kind of smart materials are available, and these smart materials has a potential application towards micro robotic related applications as well as the characteristics. Now, as far as in this particular aspect, like when we try to talk about when we try to discuss about this family of these materials, one question which comes into our mind: how do we select a particular material or a particular actuator for a particular application? So, ideally we may need to consider two important parameters. One parameter is called as a actuation stress, and the other parameter is called as a actuation strain. So, actuation stress is nothing but the amount of load applied on it, and appropriately the amount of strain which gets displaced out of it. So, based on the actuation stress and actuation strain and based on the requirement, so let me just use a fresh slide. So, when we consider smart material based actuators, and if we need to select an actuator for a particular application, then the actuation stress, it is decided based on the actuation stress and actuation strain. In addition to this, it also depends upon the responsiveness of the material. It also depends upon the overall frequency of actuation of the material. It also depends upon the overall resolution of the material, reliability and repeatability of the actuator is also considered as a key parameter for selecting certain amount of smart material for these smart material based actuator applications. Okay. Now, in addition to this, there is one more parameter which can be an energy density. Another important parameter is the hysteresis. Of course, hysteresis will fall under these categories, but ideally if we take hysteresis, hysteresis can also considered to be one of the key parameter which basically will try to create a kind of an impact on such kind of smart materials, or it can also be considered as a deciding parameter with reference to the functionality and with reference to the applications. Now, let us talk about the shape memory alloys. So, as far as these shape memory alloys are concerned, these are the materials which is responsive to heat. Okay. So, one more characteristics which also decides is the actuation medium. So, the actuation medium, like in the case of SMA, it is thermal. In certain cases, it is electrical based. That is in the case of piezo, it is electrical base. In the case of magnetostructive, materials, it is magnetic base. in certain cases like conducting polymers, or ionic polymers, or thermal responsive polymers. These are electricity based. In some cases where we have some materials are responsive to heat, responsive to moisture content, like microbubble structures. That you can take a small tissue paper and let us consider you have a cup of hot water. So, when you try to put a tissue paper on top of it, either the tissue paper folds or the tissue paper will try to fall inside the cup of the water. So, this is because like whichever steam which is getting generated, the steam will start filling up these micro bubbles. These micro bubbles get enlarged and finally it will have an increase in the density, and because of this the paper will try to fall into the liquid and it gets sinks. Okay. So, these are called as microbubble structures, and the overall medium is the moisture medium. There is a concept which is called as ferrofluidic structures. As far as these ferrofluidic structures are concerned, these ferrofluidic structures, it has a kind of magnetorheological based particle. So, what people used to do is, so they used to collect this magnetic nanoparticles and they try to mix these magnetic nanoparticles in a liquid medium, and then it is aligned or in a liquid medium or sometime in a gel medium also, and then they try to align a kind of a magnetic field surrounding the surface so that you get a kind of a spikes coming out of it. So, such kind of ferrofluidic structures are basically actuated or manipulated using a magnetic field, and then we have the hydrogels which are actuated using a pressurized fluid. So, ideally hydrogels will have a kind of a structure through which when we try to inject it, it tries to create an impact. And then we have an auxetic structure. Mechanical loading is considered to be one of the key element of this auxetic structure. Now, let us discuss about the functionality of a shape memory alloy. So, as far as these shape memory alloys are concerned, like these, as I had mentioned earlier, they are responsive to heat. So, this video will give you a clarity. So, here there is a shape memory alloy spring is there. This shape memory alloy spring is attached with a weight. So, when it is attached with the weight, what happens is there is a kind of expansion is observed, and when we try to give an electrical biasing to it, it comes back to its shape. Okay. Similarly, so that is this material is highly responsive to heat. Similarly, in this particular case, so the person is trying to have a spring and he is trying to elongate the spring, and he is putting those elongated springs in a hot water condition, and you could see it is highly responsive to heat and it is trying to take a shape and it forms a kind of a structure. Okay. Now, one of the key aspect which we may need to look into this is SMA input in terms of deformation, and the actuation is through heat, and output we get in terms of a displacement. Okay. So, if you keenly observe in this, the amount of displacement can be efficiently controlled based on the electrical biasing. That is, let us consider we are just enlarging the shape memory alloy, and we are trying to give a kind of a energize. It is completely in an elongated phase, and then when I try to supply a heat, it will try to come back to its steps. Now, the position at which it needs to come back can be appropriately restricted by applying an electrical biasing to this particular system. Okay. So, in case if I try to give a pulsed current, then appropriately I can have a control over the electrical biasing. So, this is one advantage of this system. So, like conventionally you can use a conventional heat, or in cases where you have an electrical biasing, you can also apply an electrical biasing to it to appropriately constrain the requirement what we are looking for. Like in fact, like one of the application what we had performed some experiments where we had developed a kind of a shape memory alloy based engine, so which is called as Johnson's heat engine. So, the main aspect of this Johnson heat engine is it will be having a kind of a rim with shape memory alloy springs integrated into it. So, we kept this ring near to a exhaust of a vehicle. So, what happens is there was a kind of a contraction and elongation in these particular springs, which resulted in a kind of rotation. So, you can refer to this Johnson's heat engine in YouTube. You will get lot of videos on this. In fact, this is a kind of this rotation happens because of the shift in the center of gravity when these kind of smart material based structures are integrated. Okay. Now, let us see the overall family of the smart materials, and here also based on the based on the type of the actuation. So, we try to select the shape memory alloys based on our requirement. So, ideally these shape memory alloys are classified based on the actuation temperature. If you are considering it for an actuator application, or based on the sensing window if you are considering it for a sensor. Now, there are different types of shape memory alloy materials are there. One is a copper based shape memory alloy, so which has a combination of Cu, Al, Mn or Cu, Al, Mn, Zn, etc. So, either it might be a ternary or it might be a quaternary alloy. Then there are some Fe, Mn, Al, Ni based combinations which are there. There are Ni based Husserl alloys are there. So, Husserl alloys means basically these are called kindly called as a magnetic shape memory alloys. Then quite a good amount of shape memory alloy polymers are available, and then we have a nickel titanium based shape memory alloy, and nickel titanium integrated with certain intermetallics which includes PD, PT, HF, zirconium based structures, so that appropriately it can be used for manipulating the structures. And then we have the shape memory alloy ceramics. So, many shape memory ceramics are being developed basically for some kind of high temperature applications, etc. Now, if you see the overall family of these shape memory alloys, these family of shape memory alloys are governed by the actuation temperature. So, if you see in this particular case, this is with reference to Kelvin. In the case of copper based shape memory alloy, you have a wider spectrum. So, interestingly, this works on both positive side as well as in the negative. That is, it has a capability to work in the cryogenic environment also. So, this is one advantage of this copper based shape memory alloys. Like you can work on liquid hydrogen, liquid helium, liquid oxygen, liquid nitrogen. So, in all these domains, these shape memory alloys can be actuated, and then it also has a potential application up to 250 to 350 degrees Celsius. In fact, the working window, that is the mechanism of shifting, mechanism of transition gets changed with reference to the different compositions. So in fact, it has a complete drawing, it has a complete diagram, alloy diagram, which basically talks about the composition diagram, which basically talks about the influence of the composition with reference to different temperature. Then we have an FeMnAlNi alloy. This FeMnAlNi alloy also has a wide spectrum. However, with reference to life cycle and fatigue perspective point of view, this has its own limitations. So commercially, not much FeMnAlNi alloys are not available. Many people closely work on copper-based shape memory alloys. In fact, quite a good amount of research has been performed in this particular domain. Then we have the Ni-based Husler alloys. So these Ni-based Husler alloys are also capable enough to work in the low temperature domain and slightly in the high temperature domain, but it is mainly more towards the low temperature domain. Then we have the shape memory alloy polymers. So shape memory alloy polymers are widely used in soft robotic related application, especially for gripper related applications, and in certain cases it is also used for kind of actuation related applications, and in some cases it is also used for kind of like switching related applications, etc. However, since its working window is limited, it has its own limitation towards applications. Then we have NITA structures. NITA structures are considered to be a conventionally available structures. These nickel titanium structures, like if you try to procure a shape memory alloys, most of these shape memory alloys are nickel titanium structures. In fact, on a brand name, it is called as NPTEL. So which is commercially available in the market, and it has quite a good amount of working window. On the cryogenic perspective point of view, it has a very good property in the case of liquid nitrogen environment. At a high temperature perspective point of view, it has a very good property between the range of 80 to 130 degrees Celsius. Then there are several research groups who have attempted in adding certain amount of intermetallic structures and intermetallic layers into it, which includes a PD, PT, HF and zirconium based structures to this nickel titanium based structures, so that what happens is, like, appropriately we can tune the property of the shape memory alloy and make it workable for the customized environment or the customer's characteristics what we are looking for. Next is with respect to shape memory alloy ceramics, shape memory ceramics. This is quite a challenging area. Not much work are there in this particular domain. In fact, on micro robotics perspective point of view, this is not much explored. However, like, there are some possibility, because whenever we are working on high temperature conditions, probably these ceramics can be deployed. In fact, that is the reason in most of the working window is in the range of completely close to around 400 to 500 K. So which means it has a positive domain. However, it doesn't has any kind of functionality in the case of a cryogenic system or any kind of low temperature conditions, etc. Now, these are a family of shape memory alloys. What makes this shape memory alloy capable to fall under the category of smart material for developing different smart systems? Now, like, as far as this shape memory alloys are concerned, so for that we need to understand the history of a shape memory alloy. So in fact, the first shape memory effect was demonstrated in the gold cadmium materials, on the gold cadmium alloys, where it had a kind of a pseudo-elastic behavior. So the first SMA characteristics was demonstrated in 1932. Then later William Buchler and Frederick developed nickel titanium alloys for the Naval Ordnance Lab in 1962 to 1963. This is the point exactly the nitinol came into existence. In fact, since it is called as Naval Ordnance Lab, this nitinol is derived from this Naval Ordnance Lab. So from this particular point, the shape memory alloys are considered to be a kind of a strategically driven materials, because it has a potential applications towards this biomimicking related structures, towards maneuvering the aircrafts. In fact, aerofoil structures, smart aerofoil structures can be demonstrated and developed in using this particular shape memory alloy integrated systems. There are some systems where a small micro walls and micro transducers have also been developed using these shape memory alloy structures. Now, with reference to biomedical perspective point of view, since the shape memory alloy comprises of nickel and titanium. These nickel and titanium structures are highly biocompatible. So, it can be effectively used for like a certain amount of biocompatibility related applications. So, one of the applications might be like a shape memory alloy based pins and shape memory alloy based braces, etc. are some of the examples where it has been effectively used for biocompatible related application. Most of you might have heard about the shape memory alloy based tins, which is incorporated inside the walls and as well as inside the tubes. So such kind of shape memory alloy tins can also be deployed. Now, as I had mentioned, so one is used for aeromedical and another one is with respect to biomedical device. However, with respect to micro robotics perspective point of view, like it has a capability to get manufactured in a micron level, and then the actuation can be done through an external means so that appropriately it can be opened up. In fact, there are reports on shape memory alloy based micro robots which is used for a certain amount of surgical applications, which we will be discussing in the upcoming modules. Now, what makes shape memory alloy capable enough to retain its functionality? Now, if you try to look into the fundamental behind this structure, like this basically happens because of switching between the austenite phase and the Martensite phase. Let us consider, like I have a rod of shape memory alloy. Now, this rod of shape memory alloy is initially in a Martensite phase as shown over here. Now, what I am trying to do is, I am trying to deform this rod, which I call it as a deform Martensite. So, I am applying a stress to this rod to form a deform Martensite. From the deform Martensite, when I try to supply a heat to it, it comes to an austenite phase, which is called as a parent phase. Now, on cooling it, because of the thermally induced Martensite, it comes back to the Martensite phase. So, this is a kind of cycle which is well established in the case of which is the key fundamental behind the shape memory alloy based structure. So, if you closely observe, the overall characteristics in this is stress is involved, a thermally induced Martensite is involved, and again a stress is involved. So, it is a kind of a thermomechanical effect, like I would say like a thermal effect and a mechanical effect separately are being induced into it to get the required transformation and the required actuation what we are looking for. Now, like there are, so as far as if we try to look into these fundamentals, like there is a kind of a transition phase which exhibits in all these domains. So, these transition phase play a vital role with reference to the actuation and with reference to the response time of the sensor. Like for example, if I want to use it instantaneously, it might be very difficult. Like that is the reason some of the shape memory alloys are highly restricted for a kind of a low frequency, like a maximum frequency a shape memory alloy can exert is close to around 10 to 15 hertz. However, on an energy density perspective point of view, it has quite a good amount of application as well as it has a quite good amount of characteristics. How these shape memory alloys can be developed, how these shape memory alloys can be trained, how these shape memory alloys are being effectively used for a robotic application, let us discuss in the upcoming classes.